Hi everyone. Thank you to Paul and the organizers for inviting me to give a talk. And I'll be talking about some work in progress with Pedro Simija, my advisor Brian Swingle, and Mark Van Ramsdonk. This is something that is still unpublished, but a first paper about this should be out soon. And the main questions we want to answer are, first, how can we obtain a fully microscopic description of cosmology in holography? Now, ADS-CFT gives us a nice framework to describe quantum gravity, but it still doesn't tell us exactly how to describe cosmology, so quantum gravity in a cosmological universe. And so we want to try and build up a microscopic description of that. Our attempt will be different from other trials that have been done, for example, the DS-DSS correspondence. But we'll see how our approach goes. And the other question that we want to ask her is, if we can build this microscopic model, then what kind of cosmology would that be? So what kind of errors would we have? Or what cosmological perturbations would that predict, and so on? So we will focus on these negative lambda cosmologies. Now, this seems theoretically natural in the sense that ADS-CFT gives us a framework to describe quantum gravity in negative cosmological constant spacetimes. But they are generally not very much studied because we observe in our sky a positive cosmological constant, or at least we observe an accelerated expansion that is explained in the simplest way using a positive cosmological constant. But we will see that even with negative lambda cosmologies, we can have phases of accelerated expansion. That's a known result that we will make compatible with our models. Now, theoretically, it's interesting to study these negative lambda cosmologies for the connection to ADS-CFT, but it's still not super easy to do that because these cosmologies are generally Big Bang Big Crunch cosmologies, so they don't have any asymptotic boundary where to define your CFT. But we will see that in some specific models, we have a way to look at complexified geometries that have asymptotically ADS boundaries, and so we can define there our CFT, and we will exploit this feature to try and build a microscopic model describing cosmology. And in particular, maybe I will comment about this at the end, but this also defines a special state for our cosmology. So the talk will be divided into parts. The first one will be more conceptual, will be about how these cosmologies are encoded in the microscopic setups, while the second part will be in some sense more phenomenological, in the sense that we will try and look what kind of eras and type of cosmologies can we have, and in particular if we can have an accelerated expansion. Now let me mention that I will be talking about inflation somewhat improperly, in the sense that I don't necessarily mean primordial inflation, but I mean in general a phase of accelerated expansion for the universe. So let's start with the first part and look at what the microscopic model will look like. So we call this a Euclidean sandwich. And we have two copies of a 3D CFT on our tree. And these two copies will be of a CFT which is holographic. So we have some ADS4 dual. And then we consider a 4-dimensional CFT, which can be holographic, but it's not necessary. So in general, will be non-holographic, and this will be on our 3 times an interval. And we want to pick the 4D CFT with many less degrees of freedom with respect to the 3D CFT, such that the physics of the ADS4 dual of the 3D CFTs will not be very much modified, at least in the UV. And we want to couple these two 3D CFTs at the two ends of the interval on which the 4D CFT is defined. And we want to couple it by a relevant perturbation, such that the UV physics will be unmodified, so we will still have the asymptotically ADS bound regions dual to the 3D CFTs, but we want the physics in the IR to be modified, such that we'll see that our ADS4 spacetimes can connect deep in the bulk IR and form a Euclidean wormhole. I will talk about that later. So this is the setup we should have in mind when we have a 4D CFT, which is not necessarily holographic, on an interval coupled to two 3D CFTs. Now, before we look into the dual of this picture, let me mention what we mean by slicing duality. So let's consider one of the sandwich theories where we have a Z2 by Z2 symmetry. So we have two reflection symmetries, one along the interval and one along one of their three directions. And then we can slice open the Euclidean path integral to define a Lorentzian state. So we know that if we have a Euclidean theory and a Euclidean path integral associated with that, a natural way to define a Lorentzian state of a Lorentzian theory is to slice it open on some special slice. And in this case, we have two natural ways to do that. The first one is to slice it on a slice that divides the interval connecting the two 3D CFT in half. And in this case, the interesting thing is that we don't have any 3D degrees of freedom in the Lorentzian theory. We just have a state of the 4D CFT. I will refer to the 4D CFT sometimes as auxiliary. So to the auxiliary degrees of freedom. And so the 3D CFTs only appear in the Euclidean past of the Euclidean path integral that prepares the state of the 4D excited CFT. The second slicing that we have is along a slice that divides the symmetrical tree direction in half. And in this case, we have an infinite amount of Euclidean evolution before slicing open the path integral. So we have a vacuum state. And this vacuum state will be the vacuum of a theory given by a 4D CFT on an interval coupled to two 3D CFTs. Here, at this stage, we're only looking at the microscopic picture on a boundary, so there is no gravity. Yeah, we will look at the dual in a second. So this is just the boundary theory. And so this vacuum state, in the case we're interested in, this 3D, 4D, 3D theory will confine in the IR. Now, in this case, of course, we have both 3D and 4D degrees of freedom in the Lorentzian theory because we have the 4D CFT and the two 3D CFTs at the two boundaries. We have a lot of different models, so I try to be consistent with colors. The first slicing will always be in blue. The second slicing will always be yellow, and the same is for the duals. And I will generally use red for the Euclidean theories. So before I move on to the bull dual, is there any question on this microscopic construction? So
this is the same as the bracket wormhole, right?
Yeah, this is a similar setup, yeah.
Is necessarily going to be conformal boundary conditions, conformally invariant boundary conditions?
Yeah, generally they will be conformal boundary conditions such that we prefer the 3D conformal symmetry, and we will break only partially the 4D conformal symmetry.
Is that 4D gravity?
In this case, it is just the boundary theory. Now we look at where there is 4D gravity.
You said no to 4D gravity before. That's still...
At this stage, we're only looking at the boundary theory and the microscopic theory.
Boundary is 3D plus 4D.
Yeah, the boundary is a 4D interval times R3. And at the ends of the two interval, there are two 3D CFT coupled on R3.
So we don't yet have any, not that far from that, but there's no connection to the broadcast wormhole yet.
Not yet, yeah.
And you probably don't go to that kind of higher order thing.
Sorry, I didn't catch that.
You probably don't go to those higher order things. You don't need to be bracket wormhole.
Yeah, no. Yeah, this is, I think the construction of the microscopic construction is somehow similar, but it's not exactly the same. Okay, so let's look at the Euclidean dual of the initial Euclidean sandwich theory. So this theory, the microscopic theory, will have a scale, and so in the IR will flow to some 3D CFT. The scale is just given by the distance between the two 3D CFTs. And we have two possibilities. In the first one, we flow to a theory which is gapless in the IR. And so this will correspond to having two 4D ADS4 spacetimes dual to the two 3D CFTs, and those will be will go just arbitrarily deep into the IR and will not connect to each other. The alternative to this possibility is that the sandwich theory flows into the IR to a gap theory, so it confines in the IR. And if that's the case, what we get is that our claim, and I will give a slide to gain a little bit of intuition why we claim that this is the case, we'll have a connected bulk deep into the IR. So the ADS4 dual to the two 3D CFTs will connect deep into the IR. Now, let me mention just a side comment. Won't be particularly relevant for the rest of the talk, but I think it's interesting. When we look at these duals, we don't have a 5D Boole dual because we're not considering the auxiliary degrees of freedom here to be holographic. So we just have a 4D Boole dual. But when this is the case, what we really have is not only a bulk, which is dual to the two 3D CFTs, but also a non-gravitational path that couples the two asymptotically ADS4 boundaries. So, and that will be what is, let's say, what is left of the 4D CFT coupling the two 3D CFTs in the macroscopic picture. And then we'll have some effective field theory on the wormhole, which is also determined by both the 4D CFT and the 3D CFT and their coupling. So.
Can we think of this specifically as, let's say, the CFT in 3D is the M2 brain CFT, so totally really complete example of ADS CFT. Can we have that example in mind?
Sorry, can you repeat that?
So far, this is some 3D CFT. Can I accurately have in mind the M2 brain theory, say, as an example of that, the simplest version of ADS CFT and boundary 3 dimensions?
I think so. I am not sure that, so I don't want to endorse that, but I think that might be a microscopic example of that, yes. But
so the confinement arises because of something to do with the way the interval is specified. Maybe it's sort of like Schwartz boundary conditions in some sense, and
yeah,
gives you confinement of the pair of such CFTs.
I think so. The way I understand it from an effective field theory point of view is that you have just a 4D CFT coupled to two 3D CFTs, and in that case, in the UV, this will be certainly a CFT, but when you flow into the IR, it's not guaranteed that you have a fixed point in the RG flow that brings you to a 3-dimensional CFT, but you can just have some kind of, you can just have a gap theory in the IR. So I'm not sure about specific microscopic examples of this, but I think that's the effective field theory picture that I have in mind. So about why you get a Euclidean wormhole in the dual of these, I will just give some intuition in a second. But let me say that the metric of this Euclidean wormhole will be conformally flat, and we'll have two simple poles at the two asymptotic boundaries of ADS4. So I think one of the simplest ways to understand why a gap theory would correspond to having a connected Euclidean wormhole is to consider the case when the 4D CFT is also holographic. So we have a 5D bulk. This is analogous to those double holographic setups where we have a bath, which is also holographic. And in that case, we are looking at the case where the sandwich theory is gapped. And the result is that we don't have IR physics, non-trivial IR physics at arbitrary long wavelengths. This means that the corresponding 5D bulk will be capped off somewhere in the IR. And one of the simplest ways to determine, to cap off the bulk in the IR is to consider an end of the world brane, which is homologous to the sandwich theory. And that will connect deep into the IR, cutting off part of the bulk. This is analogous to what Tagayanagi and collaborators studied for the dual of a boundary conformal field theory. So our claim is that if the 4D CFT is not holographic, we won't have this bulk, but the connected space-time will still be there, and so we will have a Euclidean wormhole just dual to the 3D CFTs, coupled by the 4D CFTs on a non-gravitational space-time.
Sorry, can you say where again the end of the world brane is here?
So the red is the end of the world brane, and that connects to the two. Yeah, the colors are not. Yeah, this red sheet is the end of the world brane, and we have an ADS5 bulk if the 4D CFT is also holographic.
Okay, so for this, you want some sort of O-plane that gives you such an end of the world.
Sorry, you want some sort of?
You want a microscopic version of this end of the world, right?
Yeah, and that will be associated essentially to the two 3D CFTs. And if we look at the ADS-B CFT construction, we can consider the CFT4 coupled to the two 3D CFT just as a boundary conformal field theory. And so the bulk dual of that will be an end of the world brane homologous to this BCFT on the boundary.
So the end of the world is the confinement. Is that what you're saying?
Yeah, essentially yes. So if you go deep into the IR, it cuts off the bulk. Okay. So, and in our case, we won't consider actually a 5D bulk. We just have, because the 4D CFT won't be holographic, but we still have a connected spacetime. So we'll just look to the effective theory on this end of the word brain without considering the 5-dimensional bulk. So we saw these two different slicing in the microscopic case, and those correspond to different slicing in the Euclidean path integral in the bulk. So the first slicing, the one that defines the excited state of for the auxiliary CFT, that corresponds to a symmetric Big Bang Big Crunch cosmology. And to see that, we can take our Euclidean wormhole and slice it along a direction with a slice that divides the direction along the wormhole in half. And then we analytically continue the direction along the wormhole to become the conformal timing cosmology. And this gives us a Big Bang Big Crunch cosmology. This is analogous to what Maldacena and Mautz did in their paper, where they consider the same kind of Euclidean wormholes and slice on a slice which divides the wormhole in half. And if the slice that we use will correspond to the maximal expansion slice, and then if we evolve forward or backward in time, you get a big crunch or a Big Bang.
Where's gravity now? I'm sorry, I keep asking questions, but
Yeah,
where
no
does
problem.
gravity come in?
So gravity here, this is in the Euclidean dual. So our gravity picture here is just looking at the effective theory of this brain without considering the 5D bulk. But so here there is the microscopic theory, which is 4D CFT coupled to 3D CFTs, and that's non-gravitational. Then we have the bulk theory, which is this ADS4 brain, and that's coupled to gravity.
Yes.
And then that will also be coupled to some non-gravitational path. In the rest of the talk, I will mention just for a second the bath, but I will be focusing only on the gravity of this brain. And this brain takes the geometry of this brain is a Euclidean wormhole, which is this one. So what I'm doing now is just taking this Euclidean gravity theory, slicing it open, and analytically continue to get a cosmology. So this is all a gravitational setup. Yeah, also this is interesting because here, what we really have here is that the two asymptotic boundaries in Euclidean signature are connected by a path. So when we slice open the path integral, we get a cosmology entangled to a path. And that's very interesting also for islands in cosmology. And I won't be commenting about that, but I'd be happy to talk about it later. So the second slicing possible is the one that defines the vacuum state of the microscopic theory. And that corresponds to an ADS traversable wormhole in the Lorentzian picture. And the wormhole has a planar cross-section. Again, we can just take the Euclidean path integral and slice it open along with a slice that divides the R3 directions in half. And we get a space-time which is connected. So we have two asymptotically ADS4 boundaries connected by an ADS in the bulk. And so we have this time a scale factor, conformal factor that is still has two poles at the two asymptotic boundaries. And so we just have an eternal traversable wormhole. So we had a lot of, colors are not showing up very well, but we had a lot of different setups here. So we had a Euclidean sandwich theory, which is dual to a Euclidean wormhole. And then we can slice it open to define an excited state for DCFT corresponding to the cosmology, or to the vacuum state of a gap theory corresponding to the traversable wormhole. Now, this slicing duality is powerful because it relates cosmology and traversable wormhole by a double analytic continuation. We saw that the metrics are basically the same metric via a double analytic continuation. And this means that if we take any correlator on the doubly symmetric slice, then that correlator will be equal in the two pictures. And in general, if we have some observable in one picture, which depends on the coordinates, that's related to some other observable in the other picture, which is just related to the first one by double analytic continuation. So what this tells us is that this cosmological physics is encoded in the 4D CFT excited state, but it will be encoded in a complicated way, and we'll see in a second why. But it's also encoded in the vacuum of this gap theory via double entity continuation. And that will help us to probe the cosmology from the microscopic point of view. So in particular, we'll see that this helps us to probe the physics behind the horizon of a black hole. And the way to see that is, again, to have a 4D CFT, which is holographic. So the auxiliary degrees of freedom are now, again, for a second, holographic. And we have an excited state of the cosmology, an excited state of the CFT that looks thermal. So the corresponding 5D ball dual, yeah, colors are not showing up at all, I'm sorry, is a Euclidean black hole, and the cosmological slicing will give us a double-sided black hole with the end of the world brane behind the horizon in the Lorentzian picture. And so the cosmology here lives on this end of the world brane. But the 4D CFT, whose excited state that describes this spacetime, is on the right asymptotic boundary. So probing the physics of the cosmology will essentially mean to look behind the horizon of a black hole, and we know that that's a highly complex task. However, if we connect through the double entity continuation to the vacuum state of the gap theory, then we won't have any, that's a vacuum state, and we won't have any, we have a traversable wormhole and no horizons. So we can just connect observables in the traversable wormhole to observables in the vacuum of the gap theory using ordinary HKLL. And so we can probe any observable of the cosmology by double entity continuing that observable and then connecting it to a microscopic observable using HKLL. And so this is a nice way to get a way around this complexity problem of probing the cosmology by passing through the vacuum gap theory.
But is that cosmology like 4-dimensional with a boundary?
Yeah, in this case, here I am again considering for a second the case when we have a 5D CFT. No, there is no connection in the cosmology between, in the Lorentzian cosmology, we have a Big Bang, Big Crunch cosmology, so we don't have any asymptotic boundary. So we don't have an easy way. What? In that slicing. Yeah.
Supposed to be that slicing, and is that
In the opposite slicing, we have the two 3D CFTs connected.
That you can get the information on the other cosmology from.
Yeah.
But it's a different, right? It's different Lorentzian continuation.
Yeah, it's a different Lorentzian continuation, but they are connected by double entity continuation. So if we have an observable in the traversable wormhole related to some vacuum theory observable, then that observable will be equal to some cosmological observable via double entity continuation.
But physics is kind of, you're doing different things.
Physics is different, but gives you the same answer. Yeah. So yeah, the takeaway from this first part is that we have a Euclidean ideas for wormhole, and that's dual to this sandwich theory. And then we can slice open the sandwich theory in two different ways. And in one way, we get a symmetric cosmology encoded in a very complex way in the 4D CFT state, so in the excited state of the auxiliary degrees of freedom. But if we slice in the other way, we get a planar ideas for wormhole without horizons, and that's encoded in a much simpler way in the vacuum state of a gap theory. And the two are connected by double entity continuation. So this means that this cosmology is dual in this precise sense to the vacuum physics of this gap theory.
But is the map only simple on 4-dimension 2 subspace?
So this is a very good question. So I think on the codimension 2 surface, the idea is that the observable are exactly equal because all the coordinates set to 0. But in general, if a coordinate is a function, sorry, if an observable is function of the coordinates, then we can just analytically continue to its Euclidean version, and then analytically continue again to the Lorentzian version. So it's just like the same way how Euclidean observables in quantum field theory are connected to Lorentzian observable in quantum field theory. And doing this process twice, we connect cosmology to traversable wormhole.
Yeah, you have to time evolve to the t equals 0.
Yes.
And then you continue it.
And then you evolve back. Yeah, that's right.
Okay.
Is there any other question on this first part before we move on to the second part?
This cosmology is this bang crunch, and it's a part of a bigger system, if I understood that correctly.
Yeah, it's okay. The bull dual is just that, but it's also this cosmology is entangled with a non-gravitational path. Yeah, and they are separated. There are no connection between the two.
So, you know, the cosmology by itself has fluctuating gravitation. That's just So I might expect some appropriate level of imprecision in the dictionary.
Mm-hmm.
So yeah, that's what I'm trying to ask here is maybe that's implicit in your HKLL reference where you have to recover the fact that
Well,
things that are in the bulk are not arbitrarily well localizable, and so that should hit you here too.
but I think that's related to the fact that we have a gravitational path, sorry, non-gravitational path entangled to the cosmology. So if we trace out the path, then we have a mixed state in the cosmology. We can have any sort of things going on there. But the two together define a pure state.
The two together, right, but just sort of isolating the cosmology is probably, I'm not saying this is a criticism against the right physics,
Mhm.
there's some level of irreducible fluctuations in that.
Yes.
Okay.
Yeah, that's right. But if we look at the microscopic picture, if we think, I think one way to understand well how the cosmology is determined by the dual picture of the, for example, the 4D excited CFT, is because if we take an arbitrary large slice, even the whole cosmology at the t equals 0 slice is completely encoded in a region of the 4D CFT using a construction like cosmological islands, for example. So I think that the physics in the cosmology, if you have full control on the microscopic setup, is fully determined. But if you trace out the path, then yes, you will see a whole number of fluctuations in the cosmology because you're basically looking at an ensemble of cosmology rather than a single one.
Sorry, you're saying the cosmological spacetime is entangled with the state of
The degrees of
freedom? Are they not the same degrees of freedom? They're not.
No, the degrees of freedom of the, so when you slice open this Euclidean path integral, and you have this first slicing, then here you also have a path connecting the two for this to the two 3D boundaries.
Yeah.
So when you slice it open, you will get a cosmological universe with an effective field theory.
Yeah.
And the degrees of freedom of the effective field theory will be entangled to the degrees of freedom in the non-gravitational path.
Are they dual to the degrees? I mean, I would say that
I think
they are the same degrees of freedom without, yeah.
if you take the degrees of freedom in the 4D path will be in a different state from the microscopic theory. It's analogous to the holographic set, to the islands case, for example, where you have a path and then you have a Boole dual with transparent boundary conditions. In that case, you have a direct connection. In this case, we don't have a connection between the two, the path and the Boole dual. But the 4D CFT state in the microscopic picture, you can compute the entanglement entropy of that using RT surface, and really gives you, the path has a double role as the 4D microscopic description, but also as a path connected to the 4D bulk.
It's a Hartmann's
Yeah.
cosmology ion.
Yeah, it's exactly the same idea of the cosmological islands.
Sorry, so the way I was thinking about this, and tell me if this is wrong. So in this picture, there's the 4D CFT.
Mm-hmm.
And if I suppose it was holographic for a second, and you're not in that case right now, but suppose it was, then there would be some like 5-dimensional ADS,
Mm-hmm.
and then this end of the world brain.
Yep.
Your cosmology is on the brain.
Yep.
And now in this case, when you're not holographic, what's replacing this like higher dimensional ADS is just some non-gravitational back degrees of freedom
Yeah.
plus the brain. So
Plus the brain.
the
Yeah.
4D CFT records this non-gravitational stuff plus the brain.
That's true, except it's not. Yeah, that's the simplest way to understand it. Except the brain will also have some effective field theory coupled to it. So in some sense, we can say that the brain encodes the 5D bulk behind the horizon, and the 4D non-gravitational degrees of freedom in some sense encode the brain which is outside the horizon. The bulk which is outside the horizon. But yeah, I think that's the simplest way to understand it, is to say that whatever was in the bulk is now, in this effective field theory picture, it's the non-gravitational path entangled to the brain, which is now this Big Bang Big Crunch cosmology.
So direct coupling could be there.
Sorry?
Direct coupling could be there.
Not really, because we don't have any ideas for asymptotic boundary here. So when you slice this open, we will have a connection in the Euclidean picture.
But now you have this, and you said that.
Yeah.
Slice this.
And then you slice that, and so you have two separated spacetimes.
Bulk, and then you said we got this bulk to be this then bulk
Yeah, if the 4D CFT is holographic, then you have a bulk in the middle.
Even if it's not holographic, some crazy degrees of freedom instead of Einstein gravity.
Well, yes, they are highly entangled. We just don't have a geometric description of that. That's what I meant,
Could
yes.
have some direction, not gravity.
Yeah, okay.
Crazy,
They are highly entangled,
Yeah.
yeah.
And in this 5D picture with a quote-unquote cosmology on a brain, that there's localized gravity there?
Yeah,
Like part of
gravity
it?
is localized that, and
So
that's,
that's a calculation you've done?
yeah, we've done a calculation of that, and it's localized via Karsh-Rundle.
That's a GDP.
Yeah.
Putting boundary degrees of freedom huge.
Yeah, we have a lot of boundary degrees of freedom and very little for DCFT auxiliary degrees of freedom, and that guarantees the localization of gravity.
I thought GDP had.
Oh, it's a huge degrees of freedom. It's kind of large kinetic down.
Yeah.
And then localizing
I mean,
gravity.
getting induced gravity that way is not trivial, but let's go on.
Yeah, so we have 10 minutes.
Yeah, okay.
It's our fault.
That's right, okay. So, okay, in the second part of the talk, I will be talking about just the bullet points of view. So we have the cosmology on one side, a traversable wormhole on the other side. And our Big Bang Big Crunch cosmologies have negative lambda, as I said, so we don't have any asymptotic ADS for boundary. And on the other hand, we have Big Bang Big Crunch cosmologies, but we observe in our skies accelerated expansion. That means that we need to account for this expansion somehow. And so one question we want to answer is whether we can have accelerated expansion in these negative lambda models. And the approach we will take is to try and find an accelerated expansion in the cosmology, but we want the traversable wormhole picture to be consistent. So we want to preserve the existence of the two ADS4 boundaries in that picture. So we will focus only on this bulk dynamics, and the bulk effective field theory in principle is completely determined by the choice of 3D CFT, 4D CFT, and coupling. I will not connect between the macroscopic pictures and the bulk pictures here, but I will just assume that we have some effective field theory in the bulk, and that semi-classical Einstein's equation hold. So we have a geometry sourced by the expectation value of this effective field theory in the bulk. Now, this is a side comment that this tells us something interesting, because the stress tensor in the cosmology bulk will be some generic stress tensor with vacuum and vacuum contributions, but in the wormhole picture, we have a static solution of Einstein's equations, and that will be just the expectation value of the vacuum expectation value of the stress tensor. So vacuum energy in the Lorentzian picture, in the Lorentzian wormhole, corresponds to non-vacuum energy in the cosmology picture. The contribution we have to the stress tensor are a radiation term, and that will come from some CFT like bulk EFT. And then we have a homogeneous scalar field in some potential. And this is the simplest possible model that can give us an accelerated expansion in the cosmology. I will work here in proper time in the cosmology, so we don't have that conformal time anymore, but we just have the ordinary proper Friedman time. And in the wormhole picture, that corresponds to a proper distance. And so the scale factor must diverge exponentially for large tau, so far away from the center of the wormhole, in order to preserve the existence of the two ADS4 boundaries.
So you've built in now a bottom-up model via phi of inflation or something in.
Yeah.
So
So we're looking.
Yeah. So we've moved well beyond the ADS-CFT version of the microscopic theory.
Okay, we should keep in mind that we have a microscopic description of these spacetimes, where we have a cosmology and a wormhole picture. And now we're trying to look directly at these cosmology and wormhole pictures to see if an effective field theory that gives accelerated expansion in the cosmology preserves the existence of the corresponding wormhole via dual double NAD continuation.
But I'm just saying, in the book, you've brought in this via phi. I'm trying to ask where that came from.
Oh, this will correspond to some operator in the microscopic CFT. And yeah, I didn't mention exactly the connection between that and the microscopic CFT. So at this stage, I'm just assuming that we can have some scalar field in the cosmology associated to some operator in the microscopic CFT. For example, this can be a 3D CFT relevant operator, and that will give us the kind of physics that we want. And that will correspond to having in the wormhole some scalar field.
Well, is VFI something with an inflationary phase?
Yeah, we'll see in a second what VFI is. Yeah, and
Okay, so I'm just saying you've taken the bulk theory and uplifted it to something very, very different from any and CFT system, which is fine, that's the right answer. But
yeah, I think it's a little bit different in the sense that in the UV will still be a CFT because we still have this scalar field will go towards, and the asymptotic boundaries will be fixed to some value determined by the UV of the 3D CFTs, but that can be a relevant operator for the CFT that then flows in the IR to some different values. So yeah, it's not an exact CFT, it's some deformed CFT.
So it sounds to me like you have a de Sitter, like you have a landscape picture where there's a de Sitter phase and then some domain wall essentially to get you to an ADS part that connects to the boundary. Is that correct? Your VFI is going to let you interpolate from something that's DS-like to something that's ADS-like.
Yeah, in the wormhole picture where we have just a DSCFT, regular DSCFT, so we have 3D CFTs connected by a traversable wormhole. What we get, we'll see in a second that. Okay. What we get is.
We've got to follow what VFI is doing there.
VFI in the wormhole picture will just be modifying a little bit the value of the scalar field along the wormhole, but just a little bit. And in cosmology picture, when we double entity continue, it will bring us an accelerated expansion.
Okay. Not forever, right? The potential goes to negative. Near the boundary has to be ADS.
Yeah, near the boundary will be ADS, and then it will have a minimum and then a max. It's a Higgs potential. We'll see that in a second.
Sorry, are you saying that there is or isn't some inflationary thing going on in the bulk, in the 4D gravity bulk?
In the cosmology picture, yes. But the cosmology picture, we don't need to connect to the asymptotic ADS for boundaries. That's what the wormhole picture does.
But asymptotic is the future and past, and then there you go to ADS. So this inflationary phase will end.
This inflationary phase will lead us from near the Big Bang towards then we have an inflationary phase and some other phases, and then we have a turning point, and from that turning point is where we connect to the wormhole picture. We'll see that in detail in a second. So in the cosmology, we just have, okay, I will go a little bit quick on this because I think I'm almost out of time. So in the cosmology picture, we'll have a Friedmann equation with a negative cosmological constant, a radiation term, and then we have the kinetic and potential term for the scalar field. And the scalar field will have the equation, Klein-Gordon equation for the scalar field will have some form which is the equation of a damp oscillator. In the confinement picture, we have an equivalent of the Friedmann equation, and the effect of the analytic continuation on the Klein-Gordon equation is to flip the potential of the scalar field. So this is important that flipping this potential will give us the kind of dynamics that we want in the wormhole picture. So in the cosmology picture, as I said, we want potential term to be dominant at some point in the Friedmann equations to give us slow roll inflation. So we need slow roll conditions to be satisfied in some region of the potential. And in the corresponding wormhole picture, we want the asymptotics to be, the ADS for asymptotics to be preserved. And that means that when we go far away from the center of the wormhole, the derivative term of the scalar field must vanish, and we must have a value for the sum of the cosmological constant and potential term at that specific value of the scalar field to be negative, such that we get asymptotically ADS. We also want symmetry for this solution, as we said, because we have this Z2 by Z2 reflection symmetry. So the derivative of the scalar field must vanish at this central symmetric point.
So your cosmology picture is kind of like creation of the universe, like Diracian from Euclidean. You create the state.
Yeah.
Equals 0, and you have inflation, and inflation ends.
Yeah.
Negative cosmological constant and crunch, right? At the end.
Yeah, that is the picture that we have in mind. Here I'm just looking at the Lorentzian case, but the slice on the state of the cosmology on the symmetric slice is prepared by basically a Hartle-looking path integral with some boundary in the passes that have no boundaries.
Difference than just the Hartle. It's similar, but it's like a Diracian thing. You can create the high potential. That's good because in Hartle-Hawking you just create the.
Yeah.
No, it's ADS.
Wait.
So it's just.
It's not Hartle-Hawking.
No.
Because Hartle-Hawking.
Yes,
Hartle-Hawking have no boundaries in the past.
Yeah, in that sense it's common, but it's not the same as.
Yeah, exactly.
Depending on how.
Okay, were you saying that in the wormhole picture you have minus the potential you have in the other picture?
Mhm.
That's
Yeah.
you have.
Yeah, basically it's the same potential. We have a Higgs potential. It's just that in the equation of motion, the Klein-Gordon equation of the scalar field, it appears with a negative sign. We just computing a Klein-Gordon equation with this. This is a spatial evolution from the center of the wormhole towards the two boundaries. And in this case, what really happens is these two terms are flipped, and the potential term stays the same. But the flipping of the potential is what will determine that we settle at the maximum of the Higgs potential that gives us the ADS asymptotics. I was about to just show a second how the evolution works in this case. So in the cosmology picture, we will start for some value of the field that gives us a cosmological inflation, just because a Higgs potential, so a quartic potential for large values of the field satisfies zero conditions. And then going on with the cosmological evolution, we have a decelerated expansion driven by the scalar field oscillating. And then we will reach the inversion point where the scalar field takes some value phi naught. Now, at this inversion point is where we perform the analytic continuation of the equations of motion, and that final data for the cosmology will be the initial data for the evolution of the wormhole picture from the central point to the asymptotic boundaries. So in this case, the effect of the analytic continuation is to flip this potential. And so we get underdamped oscillations until the scalar field fits for tau that goes to infinity. It just settles at this maximum of the potential, and we get the exponential expansion. So
The curvature of that maximum is parametrically less than Hubble's?
yeah, the curvature of this maximum is set by the ADS length of our spacetime from a microscopic point of view.
You have to model build here is the ADS for flip side of this potential. So you want a microscopic model which has the negative of this potential in ADS. That's essentially the model
Yeah.
question here.
Yeah, so the sum of this maximum of the potential plus the fundamental cosmological constant must still be negative, and that gives an effective ADS length, the real ADS length of the spacetime.
ADS for, that's what you need.
Yeah.
And you need that to happen along with the confinement and whatnot.
Yeah,
Also going
from a microscopic point of view. Yeah.
Okay.
So in the cosmology, we studied these solutions numerically. Let me skip the details, but I will just show you the numerical solutions of these equations of motion that we studied. So these are preliminary results where we see that early on, when we set these initial conditions to be large, we get a phase of accelerated expansion. This accelerated expansion lasts little just because we set the parameters for this reason, for some numerical reason that I'd be happy to discuss later if anyone is interested. But we have an accelerated expansion, then a decelerated expansion driven by the oscillating scalar field, and then we approach this turning point. And the scalar field we see here oscillates only once around the W potential, and that settles at a value which is very close to the maximum of the Higgs potential. And this is the cosmology side. So we reach this turnaround point, and then those final data are the initial data for the wormhole evolution. The wormhole evolution, so we'll have a scalar field which is at this value phi naught at the center of the wormhole, and going towards the asymptotic DS4 boundaries, it will just oscillate with damped oscillations and settle at this minimum. And the corresponding numerical solution for the scale factor, we see that we have an exponential expansion far away from the center of the wormhole, and so we preserve the asymptotic boundaries, which is what we wanted. And at the same time, the scalar field will oscillate and then die off to settle at the minimum of this potential, which is the maximum of the Higgs potential. OK, I will probably skip this comment since I'm about out of time. But let me just say that from the microscopic point of view, where you have control of the vacuum gap theory, and so the natural dual picture is a traversable wormhole, then when you then evolve backward towards the Big Bang, you have an anti-damped scalar field, and so it's kind of natural to obtain inflation while you go back in time. because the scalar field will go up this potential since it is anti-damped. So the takeaway from part 2 is that the simplest possible model that allows inflation is given by negative lambda, because that's what we want, plus radiation, plus a scalar field in a Higgs potential. And in the cosmology side, I didn't mention that, but before the expansion, the accelerated expansion, we can have a radiation era. Then we have slow roll inflation, a decelerated expansion, and a symmetric turning point. And if we keep evolving, we have the same evolution backward in time towards a big crunch. And from the symmetric slice, we can analytically continue our equation to describe the wormhole. And we have a flip scalar potential, some underdamped oscillations for the scalar field that correspond to this evolution until the scalar field settles in the two asymptotic regions to 0. And at that point, we have ADS asymptotics with an effective cosmological constant given by the sum of the fundamental one and the potential at the peak in the center. So in these microscopic models that we're treating, inflation is then possible in these holographic cosmology models, and that preserves the existence of the wormhole and the two complexified asymptotically ADS4 boundaries. So we have some open questions. I think, Paolo, I'm probably out of time, right?
Yeah, I think it's,
okay.
Yeah, but it's fine. You can
okay, just a few open questions. So one is, what cosmologies? Suppose that we have some specific microscopic theory, so a 3D CFT, a 4D CFT, and their coupling. Then it would be interesting to understand, studying specific microscopic examples, what kind of cosmology would that give rise to? Then another question is if we need primordial inflation, so the ones who solve the lambda CDM paradoxes. That is not clear here, and it seems like for most of the things we don't need it, because the microscopic theory is an underlying R3 symmetry, so it's spatially R3. So we have a flat universe naturally, and we have a homogeneous and isotropic universe. It's also in some sense to be expected to have correlations in the CMB on large scales, because those correlations in the cosmology would correspond to correlations in the wormhole picture. And in the wormhole picture, we're a vacuum state, and so arbitrary long-range correlations. And those will be inherited by the cosmology. But we might still need inflation to explain the exact type of correlations that we observe. Then other questions are how, from a microscopic theory, you study cosmological perturbations, and how you can predict structural formations and various other features that you observe in cosmology. And finally, the important question is whether these cosmologies with these features, given from a microscopic model, would match, would be possible to describe our actual universe, and so trying to match that with observational data. Of course, this is a far-fetched goal, but we'd like to answer this question at some point. So thank you. This is all I have.
So we have time for one or two questions first.
So I understood that your T equals 0 slice, where you're matching to the ADS, was actually after inflation.
Yeah.
So that means it's really different from the kind of Hawking Lincoln kind of idea where you have some simple initial state that then inflates. You're sort of setting final conditions in some sense.
Well, the interesting part is that if you take the Euclidean picture, then you can define the natural state that you define for your cosmology is the state at the turning point. Because you take the Euclidean path integral, just like Hartle-Hawking, you bring it up with some, this time with some ADS boundary in the past. And then you bring it to this natural state of the cosmology, which is where the symmetric slice is. At that point, that state will involve some kind of scalar field in this, if we have a scalar field in this microscopic theory. And then we will have this specific state for the cosmology. And then if you evolve it back in time, that will correspond to some inflation. But in that sense, you do prepare a special state for the cosmology at the turning point.
So it means that, like, the normal story about having small quantum fluctuations at early time, eventually turning into structure formation, that story doesn't go through in the same way, right? Because your small fluctuations are now at a late time.
Yeah, that's why I meant that primordial inflation is probably not needed, because we have this initial state, this state at the turning point, which is corresponding to some also vacuum state, if you slice the other way, and that will give you some specific state already at the late time. Then that might have, in some sense, a dual description if you go back in time relating to some kind of inflationary expansion. But from a Euclidean path integral point of view, the natural way to think about it is to have a special state at the symmetric slice.
Well, I have lots of questions. I mean, on Henry's point, this is a choice of state. Well, the thing about inflation is you assume the worst, and yet inflation still dilutes everything you know.
Yeah.
If you just say, oh, I'm going to start with such and such state, you would, even in inflation, you wouldn't need to solve the problem. So I resonate with that question. But let me ask something else, which is, you have this cosmology that is entangled or equivalent to the other part of the system. And in this inflationary case, it's supposed to be microscopic theory of inflation, right? One way or another, it's microscopic theory of inflation. So we do, know how to do that in, say, string theory, which is where ADS-CFT examples live, that are actually microscopic ADS-C. So, but it's, it has the feature of having, in some way that we do work out in various models, uplifted ADS-CFT. The closest you can get to ADS-CFT is do some sort of uplift of that to get some kind of inflationary phase, especially along the lift one. So I'm saying we know how to do that microscopically, but it's not a, it's a significant deformation. And so that's got to be in there here somewhere. And I'm groping for where it is in the way you were describing things.
So I honestly, I don't know the answer to the question. I think that from an effective field theory point of view, I'm not sure how exactly those deformations would come up, in the sense that it seems to me that in the traversable wormhole picture, you have basically normal ADS-CFT. You have some deformation, but that deformation is just a relevant deformation that brings the scalar field in the IR to be a little bit far away from the minimum corresponding to the CFT. But I think that then in the cosmology picture, when you evolve that, you can expect that scalar field to be going away along this relevant direction, and then to have the corresponding potential to have some minimum and then go up again. But I am not sure how to explain that microscopically at the moment. We're still working on that.
Okay, I mean, at the end of the day, we do have a microscopic complete theory of inflation in the component that's now playing the role of what used to be your picture of this constraint, right? So, and you're saying that's equivalent in, some continued wormhole setup to, something that looks different in that setup. But, yeah, I'm just suspecting there's a conservation of the difficulty.
Oh, I see. So you mean in the 4D CFT excited state, how would that look like?
Yeah, and I mean, it's interesting that you kind of translated that to some other model building question in the ADS. That's sort of what I was asking about a little bit earlier. And so that's interesting to say, okay, what is that explicitly? It sounds like it's some sort of negative Higgs potential that you're wanting to have in a microscopic string theory, Freund-Rubin sort of construction.
Yeah.
And so it might be interesting to ask, what that really entails.
Yeah. No, I agree. And also I think that how the cosmology is encoded in the 4D excited state, that's really not clear. Like it's for sure encoded in a very complicated way, and it's very non-trivial to understand that. That's why we try to make the connection to the vacuum case, where we have a much simpler understanding of what's going on to the 4D dual.
Yeah, so let's thank Stefano and